Welcome. Let's talk about solubility equilibrium today. So when we were talking about things being soluble or insoluble, we said that when things were soluble, lots of them dissolve in water. So you get a fairly high concentration of that chemical dissolving in your aqueous solution. And when something was insoluble, we said it didn't dissolve. Well, it turns out that it's not so much that it doesn't dissolve at all, it's that only a tiny amount dissolves. And so it would probably be better to call those slightly soluble substances rather than insoluble substances. They actually set up an equilibrium between the ions in solution and the remaining solid. And that equilibrium follows all the same rules that we've been talking about. So we're actually not going to do anything new today. We're just going to put it in a new setting. The first thing to recognize when it comes time to actually apply the equilibria concepts that we learned before to solubility is that the solubility equilibria are based on the dissolution of the solid. So if I have magnesium fluoride, MgF2, and I put this in water, then it's going to set up an equilibrium with the ions that will result. So magnesium and then 2 fluoride ions. Similarly, if I were to take some silver carbonate, it would also set up an equilibrium with its ions. Remember when you are writing these dissolution equations that polyatomic ions obviously will stay as a unit, but the other ions, if they have subscripts, those subscripts are going to become coefficients on the ion side and on the aqueous solution side. And these equilibria have equilibrium constants. And since this is a special application, then we're going to call these solubility product constants, or KSP, but they have exactly the same form. Products over reactants raised to their coefficients. And again, solids and liquids do not appear in the solubility product constant. So that means I'm going to have magnesium ions. You have to put the charges. Fluoride ions squared over 1. Because remember, solids don't appear. And for the silver carbonate, its KSP expression is going to be the concentration of the silver ions squared, and then the carbonate ions. If you look at the value for these solubility product constants, you're going to find that they're tiny, tiny numbers. So for example, the value for the KSP for the magnesium fluoride is 5.16 times 10 to the negative 11th. Whereas for silver carbonate, that is 8.46 times 10 to the negative 12. These tiny numbers for our solubility product constants means that we have many, many more reactants than we have products, which is consistent with the expectation that most of this is going to stay as a solid, which is the reactant side of this equation, and only a tiny bit is going to dissolve and actually become aqueous ions. As the value for your solubility product constant gets larger, you're going to have more of the ions formed and you'll have more of the solid actually dissolve. You will see values for KSP that range from 10 to the negative third, which is actually pretty soluble, to 10 to the negative 60th, where virtually none, just a tiny bit of the solid actually dissolves. So we can do all the same stuff with solubility product constant that we can with any other equilibrium constant. So if I know the concentration of the ions, then I can calculate my value for KSP. Or if I know the KSP, I can do things like predict the concentrations of ions that'll be in solution. Or I can calculate what's known as the molar solubility and the solubility of a particular compound. And the molar solubility is how many moles per liter of that solid is going to dissolve. Solubility being how many grams per liter will dissolve. The process to do all of this is going to be the same as what you've seen before. So we're always going to start with a balanced chemical equation for the dissolution and a KSP expression. We're going to create an ICE table. We are going to get expressions for the amounts of all the ions that would be present at equilibrium, plug them into the KSP value to solve for that value for X, use that to calculate our actual concentrations, and then we can do things like find molar solubility or the solubility as well. Let's work through one example so you can see how all this plays out here, and then we'll do more in class. Okay, so let's take the dissolution of chromium 3 hydroxide in water. And we're going to figure out what the concentration of the resulting ions would be along with its solubility and its molar solubility. So chromium 3 hydroxide will have the formula CrOH3, and this is going to dissolve and set up an equilibrium with its ions. Okay, not a lot of it is going to dissolve, only a little bit is. And if you look, its solubility product constant is 6.3 times 10 to the negative 31st. That's tiny. But remember, not only do we have a number for this, we can write this in terms of the chemical species. And so we know that that value will be the concentration of the chromium multiplied by the concentration of the hydroxide cubed. We don't have to include the chromium hydroxide itself because that's a solid, and that's nice because then it doesn't matter exactly how much we have. Most of it's going to stay as a solid anyway. So let's start this process by creating our ice table. Again, this is a solid, so it doesn't really matter how much we have, and we know in the pure water we didn't have any chromium or any hydroxide. But a little bit of this chromium hydroxide is going to dissolve, and although it won't show up in our KSP expression when we go to plug things in, let's say that minus X dissolves. And for these, we're always going to want the chromium hydroxide or whatever other solid we're using to be just 1X dissolving. Well, if one of those dissolves, I get 1 chromium and I get 3 hydroxides in solution, and that allows us to finish filling out our ice table. From there, I can take these expressions for the concentration of chromium and hydroxide and put them into the KSP expression. Make sure you remember to use the exponent. So in your KSP expression, the concentration of hydroxide is cubed. So here this is 3x cubed. And then we are going to solve. Once I have a value for X, then that allows me to calculate the concentration of the ions in solution. And once I have those two values, then I'm ready to determine the molar solubility and the solubility for the chromium hydroxide. The molar solubility is how many moles per liter of chromium hydroxide will dissolve. If you think about it, moles per liter is basically a molarity. And that's what we did our ice table in. So it turns out that this value for X right here, that is our molar solubility. It's how many moles per liter are going to dissolve. And I already solved for that down here. And so we can say that the molar solubility is 1.24 times 10 to the negative 8 moles per liter of this chromium 3 hydroxide. Solubility itself, it just when it doesn't say molar solubility but just solubility, that's how many grams per liter dissolve. Well, I know how many moles per liter. I can pretty easily figure out how many grams per liter just using the molar mass of our chromium hydroxide. So let's do that. So we can use the molar mass of the chromium 3 hydroxide to determine how many grams per liter that would correspond to. And a quick note on sig figs, as I look up and down this page, my KSP value had 2 significant figures. So we should make sure everything has 2 sig figs. So right here in my final answer, this is 1.3 times 10 to the negative 8th. Similarly, for my molar solubility, that should be 1.3 times 10 to the negative 8th moles per liter. And I get 1.3 times 10 to the negative 6th grams per liter for the actual solubility.